Dear students, welcome to Comprehensive Learning in Design of Concrete Structure. In this session, we are taking the part 2, what is the fundamentals of limit state method. Myself, Arjun Raj PK, Assistant Professor in Christ College of Engineering, Irinjalakuda. Before moving to the questions, we have to remember some important points about the philosophy and about the principal limit states, etc. etc. So let's move on to different points. First one, philosophy. In limit state design is a method of designing structures based on a statistical concept of safety and the associated statistical probability of failure. So in limit state method, we are designing structures based on the probability. The method of design for a structure must ensure an acceptable probability that the structure during its life will not become unfit for its intended use. Then principal limit states are, first one, the limit state of collapse and limit state of serviceability. The limit state of collapse means limit state in flexure, limit state in compression, shear and torsion. Limit state of serviceability means limit state of deflection, cracking and vibration. Then we have to move to design loads. Then what are design loads? The design loads for the limit states are obtained as the product of the characteristic loads and partial safety factors and are expressed as Fd is equal to F into gamma F, where F is equal to characteristic load and gamma F is equal to partial safety factor appropriate to the nature of the loading and limit state. While characteristic load is defined as the load which has 95% of probability of not being exceeding in the lifetime of a structure. So to make our structure safe, we have to multiply with the characteristic load with a constant. Okay. Then next slide is based on what is these constants are. What are these constants are? So for different kinds of combinations, we have different combinations of constants. So for a combination of dead load and live load, the in limit state of collapse, we have to multiply it with 1.5. So in limit state of collapse, when dead load and live load combinations are considered, it is the equation will come as 1.5 dead load plus 1.5 live load. In limit state of serviceability, it is 1 into dead load plus 1 into live load. Then when dead load and wind load are also coming, or wind load or earthquake load is also considered, in that case we have to multiply with again 1.5. Here 1.5 dead load plus 1.5 wind load. Here the constant 0.9 is not much used. In limit state of serviceability, again we are using the constant 1. So in combinations of dead load and wind load, we are using 1 dead load plus 1 wind load. Then in combinations of dead load, live load and wind load, we have to multiply it with the 1.2. Here 1.2 times dead load plus 1.2 times live load plus 1.2 times wind load. In limit state of serviceability, it is 1 dead load plus 0.8 live load plus 0.8 wind load or earthquake load. So these are the equations when we have to design a structure for collapse as well as serviceability. Please look into the equations. It is very important for different kinds of exams. It is asked several times. Okay. Then after design load, then we have to look design strength. The design strength of the material Fd is given by Fd is equal to F by gamma m. F is equal to characteristic strength of the material, and gamma m the partial safety factor appropriate to the material and the limit state being considered. So for different kinds of limit state such as limit state in serviceability and limit state of collapse, different constants are considered. characteristic strength, the strength below which not more than 5% of the test results are expected to fall. So we are overestimating the load and underestimating the strength here. That is the main thing we have to remember in limit state method. So for concrete, the constant we have to consider while determining the strength of a material for concrete is in collapse it is 1.5 and in service it is 1.0, that is 1. In steel it is 1.15, service it is 1. Then we have to by heart, so we have to understand thoroughly the assumptions used in limit state method. So first assumption are plane sections normal to the axis of the member remain plane even after bending. So it is the most common assumption we have to deal with in both the Bernoulli's bending theory as well as in limit state method. Then second one, the tensile strength of concrete is ignored. The maximum strain in concrete at the outermost compression fiber is 0.0035. So in outermost compression fiber for a beam which is loading in vertically in transverse direction, the beam will form into a sagging manner. So in that case, the top portion is under compression. So at the topmost portion, the strain will be 0.0035. In maximum condition. Fourth one, the compressive stress strain curve may be assumed to be rectangular, trapezoidal, parabola or any other shape which results in the prediction of strength in substantial agreements with the results of the test. So our concrete, based on our nature of the concrete, we have to conduct suitable test and then decide the shape of the stress strain curve. But in IS 456, an acceptable shape is provided, which is discussed in next slide. An acceptable stress strain curve is rectangular, parabolic as shown below. Here it is parabolic up to 0.002 and then considered as straight up to 0.0035 for the design purpose in IS 456-2000. Actually it is not correct actually, but it is considered as straight in for the design purpose in IS 456-2000. Here up to 0.002 it is parabolic and then rectangular variation or rectangular variation. Okay, so when there are three kinds of curve here. First one FCK, it is characteristic strength. Second one 0.67 FCK. Here and then 0.45 FCK, which is the design strength. Okay. Fifth one, the compressive strength of concrete in the structure is 0.67 times the characteristic strength of concrete. So because when we construct a cube, it will give us a FCK. It will give us a strength, but in structure it will not give the same strength because the slenderness effect, shape effect, etc., etc. So it must be we have to multiply that value with 0.67 times. Sixth one, therefore the design strength of concrete is 0.67 FCK divided by 1.5. So here in this case we have to consider the partial safety factor as discussed former. So we have to divide it with 1.5. 0.67 FCK divided by 1.5 is equal to 0.45 FCK. The design strength of reinforcement for steel reinforcement, we have to consider the again that constant 1.15. For steel the constant is 1.15. So Fy by 1.15 it is equal to 0.87 Fy. Then all the sustain curves in limit state method are considered to be elastoplastic. The curve that we have seen already. To have proper indications of failure with the cracks in tension zone, the strain in steel at a failure should be more than 0.02 plus 0.87 Fy by Es, where Fy is the yield strength of the material and Es is the modulus of elasticity, which is equal to 2 into 10 raised to 5 Newton per millimeter square. The stress strain in the steel should be more than 0.02 plus 0.87 Fi by ES, because the steel should be in the failure condition. Okay, for we are dealing in structure, the beam should be designed as under reinforced structure. That's why the steel at failure, the strain in steel at failure should be more than 0.02 plus 0.87 Fi by ES. Okay. 10th one, if the strain in steel is greater than 0.002, there will be sudden failure in compression zone of the concrete without indications. So that's why the steel in the strain in steel is kept more than 0.02 plus 0.87 Fi by ES. Okay. So it is the curve we have to consider for the steel in design, in limit state method of design. Here is the yield strength is considered as 0.2 percentage of the 0.2%. The yield stress is considered the stress at a 0.2 percentage strain. It is known as proof stress. Okay. Here first one is the original graph. Second one is the idealized graph for the design purpose. So next move on to the questions. First one, consider the following statements concerning both the working stress design and ultimate strength design of reinforced concrete. First one, the plane section before bending remains plane after bending. Second one, the tensile strength of concrete is ignored. Which of these statements is or are correct? Here options are 1 alone, 2 alone, both 1 and 2, neither 1 nor 2. Here we know that both assumptions, both statements are correct. So answer C. Both 1 and 2 is the correct answer. Both the assumptions are considered in working stress method as well as limit state method. Moving to the next question. If FCU and Fy are cubic compressive strength of concrete and the yield stress of steel respectively, and Es is the modulus of elasticity of steel for all grades of concrete, the ultimate flexural strain in concrete can be taken as. The ultimate flexural strain in concrete is 0.0035, which is clear from the previous assumptions. So answer C is the correct answer. Next one is not an objective type question. It is a descriptive type questions. And then we have to in gate as well in gate we have to work out and we have to enter the answer. Okay, we have to enter the answer in the specified column. So I have included that kind of questions too. In coming videos, I will include that kinds of questions in more quantity compared to objective type questions. Here the question is, the compressive strength of standard 15 centimeter cubes are given below. Determine the characteristic strength of concrete. Here the various samples, the one sample is given here. It is 28 Newton per millimeter square, 33 Newton per millimeter square, and 30, 80, and 40. So from this sample, we have to compute the characteristic compressive strength of concrete. So we all know characteristic strength FCK is equal to Fm minus Ks, where Fm is the mean strength, K is a constant, which is 1.65. S is the standard deviation. So we have to find out the mean strength first, then sum the given strength divided by number. It is 29.8. Then S, standard deviation. We have to find out the standard deviation. We can find out this equation from the portions in statistics. So standard deviation is root of Fm minus Fi whole square divided by root of n minus 1. So the answer is 8.03. Finally, FCK is equal to Fm minus Ks. It is 16.55. Fourth question. Combination of partial safety factors for loads under limit state of collapse and limit state of serviceability will be. Here different kinds of options are given here. then please read the options and carefully and answer the question. So after reading this and refer slide 4 and 5 also, it is there we have already discussed. Here C is the right answer. Option C is the right answer. 1.5 dead load plus live load, or 1.5 dead load plus wind load, or 1.2 dead load plus live load plus wind load in the case of limit state of collapse. Also 1 into dead load plus live load, or 1 into dead load plus wind load, or dead load plus zero point 0.8 live load plus wind load in the case of limit state of serviceability. So C is the correct answer. Question 5. As compared to working stress method of design, limit state method takes concrete to option A, higher stress level, B, a lower stress level, C, the same stress level, D, sometimes higher but generally lower stress level. The answer is option A, the higher stress level. In working stress method, factor of safety for concrete is more than that of used in limit state method. So that's why in working stress method, the size of the sections is bigger than that of limit state method. So stress allowed on concrete in limit state method will be more than that of working stress method. But in limit state method, we are taking a small factor of safety. That's why the stress allowed in concrete is more than that of working stress method compared to limit state method. Okay. Stress allowed in limit state method is more than that of working stress method. Okay. Sixth one, beam sections of reinforced concrete designed in accordance with the ultimate strength or limit state design approach as compared to sections designed by working stress method for the same conditions of load and span and the same width usually have. Option A, a larger depth and smaller amount of reinforcement. B, the same depth and same reinforcement. C, smaller depth and more reinforcement. D, same depth as that of a deep beam. Here answer is C. Lesser depth of RCC beam requires more reinforcement, both tension and compression. In the case of single and doubly reinforced, while adopting a doubly reinforced section, we have an aim. We have to reduce the size of the depth of the beam. Okay, so in that manner, we think we can assume that the lesser depth of RCC beam require more reinforcement, both tension and compression. You can calculate by using the equations also in IS 456. That kind of questions will be discussed in later videos. Okay. Seventh one, a reinforced concrete beam is subjected to the following bending moments: dead load 20 kN meter, live load 30 kN meter, seismic load 10 kN meter. The design bending moment for the limit state of collapse. So we have different types of combinations are there. So load combinations as per IS 456 2000, 1.5 dead load plus 1.5 live load, and 1.5 dead load plus 1.5 earthquake load, 1.2 dead load plus 1.2 wind load plus 1.2 earthquake load are there. So considering that we have a higher load of 75 kilonewton meter. So B is the correct answer. Okay. Next question. Question number 8. The maximum strain in the tension reinforcement in the section at a failure when designed for the limit state of collapse should be. Here answer A is the correct answer, which is in case of limit state method, the strain in steel should be more than Fy by 1.15 ES plus 1.002. So we can also refer assumptions based on limit state method. So A is the correct answer. Ninth question. The minimum strain at failure in the tensile reinforcement Fi is equal to 415 MPa of RCC beam as per limit state method is. Here also this we can adopt the same equations for the minimum strain in steel. So the minimum strain in steel should be more than Fi by 1.15 ES plus 0.002. So when substituting the value, we will get a strain which is more than 0.0037. So C is the correct answer. Okay. Last question. In a RC section under flexure, the assumption that a plane section before bending remains plane after bending leads to option A, strain distribution being linear across the depth, stress distribution being linear across the depth, both stress and strain distribution being linear across the depth, shear stress distribution being uniform along with the depth. Here, the strain distribution in working stress method as well as limit state methods is linear, but not in the case of stress distribution. So, the assumption that a plane section before bending remains plane after bending leads to strain distribution being linear across the depth. Okay, thank you. In next video, we will discuss some questions which is numerical about the singly reinforced beams. Thank you.